Hello, my name is Westman and I am a PhD student at Clemson University. The topic of my student poster submission is the overfrequency curtailment of PV generation in low inertia islanded microgrids. This work is part of a project led by TECO Westinghouse Motor Company to design a microgrid control system for an islanded upstream gas compression site. The microgrid under study is modeled in RTDS and simulation of load rejection events is performed. A frequency watt droop control is applied to the simulated PV inverter system, and the sensitivity of the microgrid frequency to the droop parameters is studied for these load rejection events. Figure 1 shows the microgrid test model, which is comprised of 4 synchronous generators, 6 induction motors, shown along the bottom, 2 medium voltage drives, which are used for starting the motors, and 1 PV system. 4 sets of simulations are performed. Each set involves a different number of online synchronous generators, 1 through 4, which effectively sets the system inertia. Summarized here are the operating points for the generators, motors, and the PV system for each of the test sets. The synchronous generators perform voltage and frequency regulation of the microgrid through use of external genset controller hardware. Figure 2 illustrates how the genset controllers are integrated with the RTDS simulation. Each test set must undergo an initialization process before the individual test cases can be performed. This involves starting the applicable number of gensets using the Woodward EasyGen Toolkit user interface, then sequentially soft starting the applicable number of induction motors with the medium voltage drives, and finally transferring the induction motors once at full load to the generator bus. During this procedure, the PV system output is continuously redispatched to maintain the generators at the predetermined load level. Figure 3 illustrates modeling of the PV system equipment and control system, as well as how the frequency watt droop control is implemented. For each test set, the load rejection event is repeated for each combination of droop slope and deadband test values. The procedure for performing the load rejection tests is shown here. In Figure 4, the frequency deviations for the single generator and 2 generator test sets are shown along the top and bottom rows of plots respectively. As expected, the maximum frequency deviations are higher for the single generator test cases. In both test sets, better response is achieved when the deadband value is lowest, which is shown in the rightmost column. However, a lower droop slope may be desirable for the single genset case to prevent overcompensation by the PV system. This can be seen by comparing the minimum frequency deviations of the top and bottom plots for each value of deadband. On this slide, Figure 5 presents a comparison of the 3 generator and 4 generator test cases, which are shown along the top and bottom rows respectively. Similar results are observed for these test cases as with the 1 and 2 generator test cases shown on the previous slide. For the 4 generator test case, the minimum deadband and maximum droop slopes may be applied without causing overcorrection in the microgrid frequency, as can be seen from the bottom rightmost plot. In conclusion, the unidirectional frequency watt function is demonstrated to significantly reduce the maximum frequency. Also, the frequency watt function parameters should be actively updated based on the available inertia due to synchronous generating units in current operation. This concludes the presentation. Thank you very much for watching.